In our discussion of trig ratios associated with right triangles, we sort of limit the value of the angles involved because within a right triangle, the angles can take on values only between 0 and 90 degrees. And so we kind of have a little limitation there on the values of those angles. Well, if we put the situation onto a coordinate plane, we can extend our notions a little bit. Now, in putting an angle onto a coordinate plane like this, we can think about a right triangle configuration by just taking a point on this ray and dropping it down to the x-axis. All right, now a right triangle is formed, and the distance here is x, and the distance here is y. The coordinates of that point would be x, y, of course. Now let's call the distance here from the origin to that point r. Now we can easily calculate the value of r from the values of x and y by using the Pythagorean relationship or simply the distance formula, and those two are very closely related, as we might realize. But at any rate, with this idea, with a horizontal distance of x and a vertical distance of y, and a right triangle formed here, we can talk about our trig ratios in the context of this kind of triangle. So the sine of theta then would be, well, let's see, opposite over hypotenuse, well, that would be y over r. And then cosine theta, adjacent over hypotenuse, that's x over r. And then tangent theta, well, that's y over x. And then the other three trig functions come directly from these as reciprocals. Well, we can then extend the angle theta into the second quadrant. You see, what if we think about an angle like this? And here is that angle theta. Now, to create our right triangle situation, we can take a point on the ray and just drop it down to the x-axis, and we have a right triangle formed, and we have a little reference angle here. Now, if this is theta, we might call this angle theta prime. You see, and then now we can theta prime like that. And we can think about our ratios in a way similar to the ratios over here. After all, this is an x. Now, it's negative in this case, but this is a y, and this is our r. You see, and so we still have the same ratios holding true. Same idea if we drop down below here. If we turn an angle, excuse me, let me get an eraser here. If we turn our angle all the way over to a point, oh, let's say right in here, then this is our angle, and now our reference triangle is a triangle formed by just drawing a segment up to the x-axis. A right angle is formed, and we have the r here, we have the x here, and we have the y here. Now both x and y are negative for this particular triangle and for our trig ratios, but no matter, we have our ratios available to us by referring to this little triangle. Okay, now with that in mind, let's talk about the sign, S-I-G-N, sign, of our trig ratios as we move around the coordinate plane. And it turns out that that SIGN changes from quadrant to quadrant. Now we know that sine theta is y over r. Now r is always positive. We'll consider it to always be positive because after all, I mean, if we're thinking about using the Pythagorean relationship to find r, and let's come back over here and understand what we're talking about here. R squared is equal to x squared plus y squared. That's a way of looking at it. So r then is the square root of x squared plus y squared. Now it doesn't make any difference whether x and y are positive or negative because they're being squared, you see, in the calculation of r. And so r will always be positive. Okay. We consider that to be the case, and now if sine theta is y over r, then in what quadrants would the y value be positive? Well, y refers to vertical distance, and the vertical distances are positive above the x-axis. So the sine of theta, because it's that ratio, the sine of theta is going to be positive in this quadrant, positive in this quadrant, but negative in these two quadrants. And let's understand why, because it's y over r. And in a quadrant down here, for example, we're talking about, you see, a y distance that is negative you see, over the r that is always positive. So in these two quadrants, we have negative values for the sine of theta. For cosine theta, now remember, cosine theta, we said x over r, and we just have to decide the quadrants in which x is positive versus negative. Now it turns out that x is positive for the two quadrants to the right of the y-axis. So we have a positive cosine of theta in these two quadrants, but negative in these two. For tangent theta, now tangent is, remember, it is, well, let me think about it a minute. And when you think about it, if you get confused about it at all, just refer back to our original drawing. Just imagine that, okay, we have this situation, we have this situation, we have a little right triangle here, and we have, from the perspective of that angle, we have opposite over adjacent. Oh, that's y over x, you see. And it takes away from the idea that you have to memorize a great deal of stuff if you can kind of refer to something to help along the way. Okay, so we have y over x, and now we have this, we have the sign, the SIGN, of both y and x to consider here. Now, in the first quadrant, both x and y are positive, so this fraction will be positive. In the second quadrant, x is negative, but y is positive. A sign difference, you see, so tangent, because it's that ratio, is going to be negative. In the third quadrant, both x and y are negative. Negative divided by negative will be positive for the tangent of a theta that falls in this quadrant. And in this quadrant, the x is positive, y is negative. We have a sign difference, and therefore the tangent of theta will be negative in the fourth quadrant. Now, we use this information like this. Suppose we know that tangent theta is negative 4/3 and cosine theta is positive. We'd like to find sine theta and secant theta. Now, basically, to find sine theta and secant theta, we need to be looking at ratios, and they are ratios, and therefore we need to be looking at lengths of sides. So we need to structure a triangle somewhere. Now, we may know already that because the tangent of theta is negative, that we're situated in one of two quadrants, but which quadrant are we located in? And we can analyze it in a number of different ways, but one way to think about it, and I caution you to be very careful here at first, that when we're talking about tangent theta now, and we know it's opposite over adjacent, but when we're thinking about an xy pair, it's y over x. And now we know that it's negative 4/3, so it could be negative 4 over 3 like this, or it could be 4 over negative 3. Now, which one is it? Well, the second part of the information will tell us, but these are our two options right now. Just knowing this, these are our two options. We're thinking, gee, I could have, let's see, a y of negative 4 and an x of 3. That's an x of 1, 2, 3, and a y of negative 4. You see, so here, so one, it could be in here for our reference triangle, you see. Or it could be 4 over negative 3. Now, the negative 3 is the x, so x is negative 3. And y is 4, so it could be here. You see, maybe this is our angle, and this is our reference triangle. Now, which one is it? Well, let's decide by looking at cosine. Now, cosine theta, remember, is adjacent over hypotenuse, but the adjacent side, when we're talking about xy pairs here, is x over r. We know that r is always positive, so in what quadrants would the x be positive? Well, x is positive over here. That is, cosine theta is positive in these two quadrants. So, aha, if we're going to meet the constraints of this, then we're in this, we have this fourth quadrant situation going on. Okay, so we have an x of 3 and a y of negative 4. All right, now I'm just going to rebuild that, that diagram. Now this is our angle, and this is our reference triangle, and this distance is 3, this is negative 4, and we can easily find the distance r here. After all, it's using the Pythagorean relationship, 3 squared 9, plus negative 4 squared 16, 9 and 16, 25, square root of 25, 5 for the value of r. Now we can find sine theta and secant theta. Sine theta Let's see, from the perspective of this little reference angle, you see, in order for us to use the triangle, this reference angle, we have, let's see, the sine of this angle is opposite over hypotenuse, so -4 over 5, -4/5. For secant, now you may use as a memory crutch for secant that it is the reciprocal of cosine. Now cosine from this angle's perspective is adjacent over hypotenuse, so it'd be 3/5. But secant is the reciprocal of that, so it would be 5/3. Let's talk about reference angles and how to make the calculation of reference angles. That's going to come in handy here in just a little bit. We know that that if we're in the first quadrant, that we're thinking about our angle theta just right here, and that's all there is to it. We just choose a point on that ray, drop a segment down to the x-axis, and away we go. But we need, as that angle theta moves into the second, third, and fourth quadrants, we need these reference angles and reference triangles to help us with our problems. If we're over here in the second quadrant, and this is our angle theta, then this would be our angle theta prime. Now to calculate it, just realize that the straight angle here is 180 degrees, and this angle theta has some value, so just take the value of theta from 180 degrees and we have this theta prime. We have theta prime. Now if we're in the third quadrant, say an angle like this, and here is our angle theta. Theta prime is the angle, well here's our right triangle. Here's our theta prime right in here. You see it's this angle. I ought to put it right in here. So there's our theta prime. But to find its value, to find the value of that little angle, we take the angle theta and subtract 180. So in one situation it's 180 minus theta, and in another it's theta minus 180. You see, it's that kind of idea, and that's what we're dealing with for all of these situations. And if we're going all the way around here, we're turning that angle all the way to here, then here's our reference angle, you see, and here's our reference triangle. And so in order to find this angle, the value of this angle, we have to take 360 degrees, the whole circuit, you see, and subtract the angle theta. So that's the idea in all of the various quadrants. Let's go through the calculation a little bit. If we want the reference angle associated with a theta of 160, then we would think about it like this. And I suggest that you make a little diagram for all of these problems, at least at first, until you really get the hang of it and you're comfortable doing it without the diagram. And you may never find that comfort, but that's okay. Just make the diagram every time. All right, so we would have something like this. So we have an angle of 160. Now here's 90 degrees, here's 180, so 160 falls into the third quadrant, and it's, roughly something like this, I guess. So here's our 160 degree angle. Now we want the reference angle here, the theta prime, and it's 180 minus 160. You see, 180 minus 160, that's 20 degrees. So theta prime then is 20 degrees. Now for a theta of 230, well, let's see. 180 would be to here, and 270 would go to here, so 230 is somewhere in the middle. So it's in the third quadrant. So here's the angle, which is 230 degrees. Now we want this angle. So we take 230 and subtract 180. We subtract the angle to here, and we'll have what's left in here. All right, so let's see, 230 minus 180, that's 50 degrees. So theta prime is 50 degrees. When we're dealing with pi in the description of the angle, and therefore we're talking about radian measure, it's a very similar idea. We just have to put our head into that kind of arena. And to do that, just realize the primary markers in our coordinate plane. Now we know those markers in angle measure to be 90 degrees, 180 degrees, that's 90 degrees, 180 degrees, 270 degrees, and all the way around is 360 degrees. In radian measure, remember this was pi, this is pi over 2, Now pi over 2 though, sometimes it's 1/2 pi or 0.5 pi. That's a nice way to look at it as well, because sometimes we're not dealing in the fraction mode, we're more dealing in the idea of decimals. And here, if this is a 1/2 pi and that's another 1/2 pi, this would be 1 and 1/2 pi. You see, or 1.5 pi. Or 3 pi over 2, or in other ways to view it as well. And this then is either 0 or 2 pi all the way around. So now when we're figuring references, we do the same thing that we did before in utilizing the 180 degrees, we're going to utilize pi. So here, if we're talking about 0.7 pi, now 0.5 pi is right here at 90 degrees. So 0.7 pi would be something like this. You see? And so let's see, now we want our reference to be over here. So what we do is we take pi and we subtract the 0.7 pi. See, that's 0.7 pi. So pi minus 0.7 pi is, 0.3 pi. You see, and so theta prime is 0.3 pi. And let's see, 1.8 pi. Well, where are we in the coordinate plane? Here's pi, that's 1 pi. Now, this is 1.5 pi to here, if the angle is turning all the way around here. You see it's 0.5, then 1 pi, and then 1.5 pi, 1.5 pi. And then, so 1.8 pi would put us into the fourth quadrant. And it would be something like this. So there's 1.8 pi. Our reference angle is here. So we're going to take the 2 pi and subtract 1.8 because 1.8 goes around to this spot. And so our angle in here is 0.2 pi. So theta prime is 2/10 pi. Now for negative angles, it works pretty much the same way. I mean, we just have to consider what quadrant we're in and look for that reference angle. If we're talking about a theta of negative 50 degrees, then from the perspective of here and turning the angle down this way, you see in the negative direction, that's what we're doing. Let me clean it up a little bit. So we have, see, from here we're turning the angle down this way 50 degrees. And so we would have something like this. This is a negative 50 degree angle. But for our reference triangle, gee, all we're doing is using a reference triangle right here, and therefore all we want is this angle. And when we talk about triangles, we talk about positive angles, and so it's just a 50 degree angle. So theta prime is 50 degrees. So that one's pretty trivial. How about negative 140? Well, let's see. From here, negative 140, going in the negative direction 140, it's like here's negative 90, and then here's negative 180. So negative 140 would be somewhere in this neighborhood. So here's negative 140. Now what we'd like is the angle that's right in here for our theta prime. And let's see, so we take our 180, you see, and subtract the 140, and we get a 40 degree angle, so it's 40 degrees in here. So theta prime is 40 degrees. Let's see, if theta is negative 1.7 pi, okay, well now we're changing, we're switching gears into our radian idea, and here we would have negative 0.5 pi, negative 1 pi, negative 1.5 pi, and then negative 1.7 pi would put us into the first quadrant. So this is, all of this around here is negative 1.7 pi. All the way around is negative 2 pi. So it's like taking 2 pi and subtracting 1.7 pi, we get 3/10 pi. So this angle is 3/10 pi. Now, if you're looking for a formula for each of these, and I don't think you ought to look for a formula. I think you ought to work these problems intuitively, kind of as I have done here. I was thinking, let's just take the 2 pi and subtract 1.7 pi to get the difference and therefore this reference angle. Now, what we are really taking is the difference between negative 2 pi and negative 1.7 pi. And we want that relative difference to be written in a positive form, you see. So, and we could write a little formula for it if we want to, but I think intuitively we can get at it much faster. Pick up your calculator and let's consider a 160-degree angle and its reference of, well, let's see, 180 minus 160 would be 20 degrees. So the angle in here is 20 degrees. Now with your calculator, find the sine of 160 degrees and the sine of 20 degrees. The sine of those two. Do you see that they are the same? You see, and because they are the same, exactly the same within the calculator, and the calculator knows all about angles that are either positive or negative, greater than 90, all of that kind of stuff, the calculator knows everything about it. But because of that kind of situation, and the notion of our reference angles, some of the angles that we deal with are the ones that have some familiarity to us. That is the 30-degree angle, the 60-degree angle, and the 45-degree angle. And we have little reference triangles to make the exact calculation for sine, cosine, tangent of all of those, and then the reciprocal functions as well. But here's how we can deal with situations involving references like this with our familiar angles. It's that the sine of 30 degrees we know is 1/2. Now, to find the sine of 150 degrees, and we can just imagine then the reference angle for this is, let's see, 180 minus 150, oh, it's 30 degrees. You see, so it's the sine of 30 degrees or 1/2. Now the only trick here in doing this kind of thing is to realize what quadrant we're in. We have to realize that if for the sine function, the sine pattern, S-I-G-N pattern is, well, let's see, we have to remember that it's y over r, and y is positive in these two quadrants, so the sine of angles is positive in those two quadrants but negative here. So the sine of 150, because 150 is in the second quadrant, it's going to be positive. Now, once we drop down here, the value is going to be negative. So when we talk about the sine of 210, you see the reference angle is going to be 210 minus 180. That's 30. Okay, so the sine of 30 degrees we know to be 1/2. But because this angle of 210 falls into the third quadrant, you see, the sine of 30 degrees in the third quadrant turns out to be negative, so it's negative 1/2. And for the sine of 330, well, 330 degrees is in the fourth quadrant, and the reference angle is, well, let's see, 360 minus 330, that's a 30-degree angle. But we're in the fourth quadrant, and the sine function is negative in the fourth quadrant, so again, we get negative 1/2 for the sine of 330 degrees. When we started our discussions of right triangle trigonometry, we talked about right triangles and various trig ratios involved within the right triangle. And because we were kind of confined to the right triangle, the size of our angles were a little bit limited. We were limited to angle sizes between 0 and 90 degrees. Well, we extended that idea by introducing the coordinate plane and turning angles in the coordinate plane, and then talking about reference angles and reference triangles, and then we could once again jump back into trig ratios using those reference triangles. Okay, we've examined those things. Now, I want to run through a discussion here and emphasize two things. I want to talk about what happens at those values of theta that are like 0, 90 degrees, 180. You know, we know what happens between 0 and 90 degrees, but what about at 90 degrees, you see, and that kind of thing. That's one emphasis. And another emphasis is I want you to get a feeling for the flow of and the change in the values for sine theta, cosine theta, and tangent theta as we move throughout the coordinate plane. What values can the sine of an angle take on? That's the emphasis here. That's one of the two. Okay. We're going to do it this way. I'm going to introduce a unit circle here, or use a unit circle for this purpose. If we're thinking about an angle theta right here, then we know that anywhere along this ray, we can choose a point and just drop a perpendicular down to the x-axis for the purpose of generating a right triangle. All right, I'm going to choose to make that point fall right here on this circle, and the radius of the circle is exactly 1. Now that allows for some convenience here in discussion. I could make it right here, and the ratios would be exactly the same as the ratios would be at any other point on this ray. As long as that angle is the same, then the ratios are identical all the way along this ray by choosing points all the way along this ray and dropping perpendiculars down here. So there's no loss in the generality of the discussion by making the point right here and the right triangle right here and this radius being exactly 1. Now the convenience of that is that sine, you know, is opposite over hypotenuse. So here we have an opposite, the y component, you see, for the coordinates of that point actually, and it's y over 1. But if it's y over 1, it's simply y. So we can just think about changes in the value of y in our discussion about this changing and dynamic situation involving the sine of angle theta. We're just going to move theta around and see how y changes. That's all we need to do. Now let's realize we're talking about a unit circle here. And so this distance is 1, that distance is 1, this distance is 1, that's 1, you see, all the way around. Okay, now with that in mind, let's see what happens to the value of y and therefore the value of the sine of theta. Okay, think about taking theta and making it smaller, just squunching it down a little bit here. And then if we're at a point of a theta of, this small, you see, then we have a right triangle right here. And notice the value of y. That's what's so important here because y is sine theta in this situation. All right, so the value of y is getting smaller and smaller and smaller. And indeed, when theta becomes 0, y is 0. You see, so the values for y begin at 0 here with a 0 of the angle theta. And then as theta gets larger, 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 the value of y gets bigger, 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 and therefore the sine of theta is getting bigger, bigger, bigger. But how big can it get? Well, it gets right up here to, in this neighborhood, you see it starts to approach, this y starts to approach 1, you see, and when we get to 90 degrees, it's exactly 1. And so the value for sine theta, that is the value of y, is changing from 0 to 1 in the first quadrant. Okay, 0, 1. All right, now, in the second quadrant, we turn angles into the second quadrant. We think about reference angles. We think about reference triangles. Okay, so very similar idea. It is the y over the radius of 1, so it's simply y. Now what's happening to y? It was 1 right here. Now it's less than 1. You see, and then for triangles down here, less than 1. You see, and actually approaching 0 again. So in the second quadrant, we're going from a y of 1 down to a y of 0. So in the second quadrant, we go from 1 to 0. In the third quadrant, we go from 0. Well, let's see, where are we going over here? A little reference triangle will help us tell. Now, the angle is this angle, but the reference angle is this reference angle, and here's the reference triangle. All right, now what about this value for y? Well, it's negative here because we're below the x-axis. And it's getting negative, and it's going to -1. You see, so it's the idea that as we turn that angle around here and the reference angle gets a bit bigger, then our triangle looks like this, and the value of y is getting a little larger negatively. And it gets larger negatively to the point of being -1. All right, so in the third quadrant, we're going from a 0 to -1. In the fourth quadrant, here's what's happening. You see, we're turning the angle all the way around here. Here's our reference angle, though, and our reference triangle. And the value of y is coming back to 0. So it's going from -1, and here we're approaching 0 again, you see, and then, bam, back to 0. So in the fourth quadrant, we're going from -1 back to 0, all the way around the circuit. All right, in a similar way, we can analyze changes in cosine theta. Now, if you forget, and you will forget, that sine 90 degrees is exactly 1. You're going to forget that. But you may not forget the idea of how we can analyze that using a diagram such as this. Just generate the notion of a triangle in a unit circle, and this will come back to you very quickly. Okay, for cosine, here's how it works. Very similar idea. We have a unit circle here. We're talking about an angle, theta, and we know that we've got a triangle in here, and we know that cosine is adjacent over hypotenuse, but the hypotenuse here is the radius of the circle, and the radius of the circle is 1. So it's an x component here over 1. X over 1, gee, that's simply x. So all we need to do is analyze what's happening to the value of x as the value of this theta angle changes from 0 all the way around to 360. Okay, let's go. We have, now notice that at 0, when this angle squunches down, the triangle gets really, really small right in here, but the value of x is approaching 1. And indeed, when the theta is 0, x is 1, and so we start at 1 in the first quadrant for the value of the cosine of angles. All right, and then as that angle gets larger and larger like this, the x component, the x part of it, is getting smaller. And actually at 90 degrees it gets small down to nothingness. So in the first quadrant, the cosine of theta is changing from 1 to 0. In the second quadrant, look at what's happening to x. You see, and that's all we have to consider here. So the x component here is negative. You see, so it's 0 right here at 90 degrees, but it becomes negative, and it grows and grows and grows out to negative 1 here. You see, it's approaching negative 1 for angles that are approaching 180 degrees. And at 180 degrees, the cosine of theta is exactly, well, let's see, negative 1. So we're going from a 0, now remember, we're talking x's here. We're going from a 0, a horizontal distance of 0, to a horizontal distance of negative 1. All right. And then in the third quadrant, we're turning angles beyond the 180 mark, turning angles like this. So we have a reference angle here, we have a reference triangle here, and the value of x is the cosine of theta. And it is going from a negative 1 and coming back to 0 in this quadrant. So it's negative 1 to 0 as that angle increases and the triangle moves like this. All right, so that, and here's what I'm talking about. That triangle is moving, kind of like this. Moves along here, this vertex point is moving just along that circular path. And just imagine that happening and how the value of x is going from negative 1 and moving back to 0. You see, and then boom, we come over to the other side, and we can imagine that triangle. You see, and how it's moving in this direction. It's going from a 0, horizontal distance of 0, and it's moving out to 1. So in the fourth quadrant, we're going from 0 to 1. Okay, I think it's important for us to realize that the values that both sine and cosine can take on are simply numbers from negative 1 to 1. That's the important idea here. That's the great emphasis of this discussion. And the other idea is, what is the value of sine and cosine at points like a theta of 0 and 90 degrees and 180 and so forth? And again, if you forget, just draw the reference triangles and think about the x and y's. Okay, now for tangent. Tangent, you know, well, let's think about it. Again, we're going to use a unit circle here, angle of theta, and we know that the tangent of theta is y over x. Oh, we're not even using the unit circle idea. We're not even using the notion that this is 1. That doesn't help us a great deal in this fraction. But we can analyze how the values for tangent will change in each quadrant. You see, because y over x, if we are talking about, and let's think about unit circle here, because as that angle gets smaller and smaller and smaller, the x, you see, will approach 1 here, and the y is approaching, well, let's see, it's approaching 0. You see, so it's, and right here at a theta of 0 degrees, y is 0 and x is 1. 0 over 1, oh, that's 0. So the value for tangent begins at 0 when theta is 0 degrees. So let's see. Now let's see what happens as we get bigger, bigger. Okay, as the angle gets larger and larger, and let's just emphasize it up here, the y is approaching 1. But the x is getting smaller and smaller. Now, what happens to a fraction whose denominator is getting tiny? I mean like tiny, like this kind of thing. And imagine even closer, smaller and smaller and smaller values for x. And that x is in a denominator. Now, tiny goes into even a number as small as 1. You see, and y is approaching 1. But it's still a relatively fixed value. It's in the neighborhood of 1, let's say. But x is getting smaller and smaller and smaller as that angle approaches 90 degrees. And it'll go into that numerator more and more times. So the fraction is approaching actually infinity as we get really close to 90 degrees. So we're going from 0 to infinity in the first quadrant. And in the second quadrant, we start out at infinity. And where are we going? Well, let's see where we're going. Now, we've got our triangle like this. Here's the y, here's the x. The x is negative, the y is positive, so we're going to get negative values. But what are we approaching here? The x is approaching negative 1, but the y is approaching 0. So it's infinity down to 0. And actually, it's negative, I should say negative infinity to 0. All right. This will be interesting graphically, won't it? When we get to graphing this, it's going to make for an interesting curve. All right. At any rate, so that's what's happening in the second quadrant. Now notice that we have negative values here, and we knew that before. We have positive values for tangent in this quadrant and this quadrant, but negative values in the second and fourth quadrants. Okay. In the third quadrant, here again we have our reference triangle, and we have a y over x. All right, the y is negative, the x is also negative, you see, and therefore we have a positive fraction here, which is predictable. And let's see, we're going from a 0, you see the value of y was 0 here, and so we start out at 0, and where are we going? Well, once again, we go to that place where the value of x is getting smaller. And it's a negative value, but it's getting really close to 0 here. It's getting tiny, tiny, tiny. So it's getting real tiny, and the fraction then becomes big, big, big. So this rascal is going from 0 to infinity. You see, and then over here, it's a very similar idea. The x is very small right in this neighborhood. That is for angles that are like this, reference angles that are in here, reference triangles that are in here. The x value is relatively small. The y value is in the neighborhood of -1. You see, but, and so a positive and a negative make for a negative outcome, you see, for the fraction. But the idea is that we're going to a point of 0 here for y. Now notice that it's y over x. The x is approaching 1, and the y is approaching, you see our vertical distance is approaching 0. So that's the numerator up here. So we're going from infinity to 0. And let's see, it's actually negative infinity, I should say, to 0. Okay. Wait a second. I need to restate something here. I'm generalizing at the points where x is 0, and I should be specific at those values. I don't want to move over to the next problem just yet. When x is exactly 0, that is, when we have a 90-degree angle and x is exactly 0, I say 0 to infinity. Well, we approach infinity, but when we get right at 90 degrees, we're not at infinity. Infinity is not an actual real number, but our denominator becomes 0. And when the denominator becomes 0, the situation is undefined. So the tangent at 90 degrees is undefined. Now, so we're going 0 to infinity, but at the 90 degrees, we're undefined. So the tangent of 90 degrees is undefined. Now, we might have been tipped off to the idea, as we're turning this angle, and we're just kind of flowing with the angle, the angle is just changing by a little bit every time. We go from 0 to infinity, and all of a sudden over here, it's negative infinity to 0. How did we jump from infinity to negative infinity? That's a leap. You see, it's the idea that we're going to have an asymptote here with our graph. But at 90 degrees, the value of tangent theta is actually undefined. And actually, I should put a theta up here. Okay. So the tangent of the angle is undefined when theta is 90 degrees because x is 0. And again, at 270 degrees, x becomes 0. You see the horizontal distance is 0. The fraction then is undefined. So down here at 270 we have an undefined situation as well. Okay, now let's jump into the next problem. I'm going to assume that of all the things that we've talked about, that you may have forgotten some things. And you may not recall every little nuance of every discussion that we've had. I think that's kind of a predictable situation. My students, for example, have trouble remembering things that we've talked about. And how do you recall those? That's the technique that I want to emphasize here. That it's okay if you forget some information. You're not supposed to go and memorize a whole bunch of stuff in order to understand trigonometry. The word understand is the operative word here for trigonometry. You base your understanding on some critical information, and that information has to do with the trig ratios, number one. You do need to remember those, and at this point with all of the practice that we've had with them, you probably already know them. And I think you can reduce the amount that you remember just by remembering the ratios of sine, cosine, and tangent, and just remember that the other three are reciprocals of those first three. All right? And if you know those reciprocal relationships, then you're fine. All right, the other idea is that we talked about some sort of familiar or reoccurring angles, 30 degrees, 60 degrees, 45 degrees, and we talked about sine, cosine, tangent of those three angles. And we said that we ought to commit those to memory. Well, maybe and maybe not. Well, even if they're not in memory, though, we can recall them by using the sketches of them. And that's what I want to show you right now. How do we analyze a situation like this? Now, let's suppose that we can't use our calculator. If we can use our calculator, we can perform the operation in about 5 seconds. But let's suppose that we can't use the calculator. We want to make the calculation by hand, and we should be able to do that even though we have calculators at our disposal. It's important to be able to analyze through this because we have a better concept of the whole idea if we're able to do that. Okay, cosine of 4 pi over 3. Well, now I'm going to think through it as you might think through it, and I'm forgetting a lot of information. Okay, so I might think, well, I know that when pi is involved, I'm talking about radian measure, so I might think of this as cosine 4/3 pi, and I want to kind of separate my thinking like that because I know that in the coordinate plane I have some points of pi and 2 pi, and those are really important points on the overall coordinate plane when I turn angles of those sizes. Okay, so this then is now 4/3. 3 goes into 4 one time with 1 left over, so this is 1 1/3 pi. Oh, good. Now I can think about the coordinate plane. And I know that this is pi, this is 0, and it's also 2 pi, if I go all the way around, okay, in terms of radian measure. This is pi over 2, okay, good. Now, 1 1/3 pi. 1 pi would be an angle to this point. 1/3 beyond that, 1 1/3 pi, you see, would take us around to, oh, maybe right in here. Okay, good. Now we have an angle in the third quadrant, okay. And I have a reference angle right in here. And I can think about a reference triangle if I want to. And now, this reference angle, how big is that angle? Well, let's see. This is 1 pi. The whole angle is 1 and 1/3 pi. So I take 1 and 1/3 and subtract 1 pi, and I'm left with 1/3 pi. 1/3 pi, okay. So our reference angle here is 1/3 pi, or simply pi over 3. Wait a second, I recognize that as one of the familiar angles I was supposed to remember the value of, but I don't remember the value of it. What can I do? Well, you know, I kind of have a feeling for the angles in degree measure a little bit better than the angles in radian measure, because maybe we've been using those a little more frequently. So what I can do about that is this. I can think, well, let's see, I know that pi corresponds with 180 degrees. And even if I don't remember the formula for changing from one kind of angle to another, I can understand the problem this way. Pi over 3 is what I'm trying to figure out. Now, from pi to pi over 3, I'm dividing by 3. If I divide by 3 over here, I find this to be 60 degrees. Oh, this is the 60-degree angle that corresponds with pi over 3. Now, I could put that back into my diagram, but I know that cosine of the angle pi over 3 is the same as the cosine of 60 degrees. All right, now, I've got a little situation going on with both the calculation for the cosine of 60 degrees as a reference angle of the triangle, and also the sine associated with the situation. The sine. Well, let's analyze what the sine pattern is. I forgot what it was. Okay, I know that cosine is adjacent over hypotenuse. So I've got the adjacent side is an x value, and the hypotenuse is always positive when I'm talking about turning angles and reference triangles and so forth in the coordinate plane. So the x, though, is negative. So cosine is negative here. Oh, now I remember. It's the x idea, and so, whoops, it's the cosine of angles in the third quadrant are negative, and also negative in the second quadrant, but positive in first and fourth. Okay, I remember that now. All right, so I know this much, that the cosine of this angle is going to be negative, and now all I have to do is figure out the cosine of 60 degrees. Well, I forgot what it was. Okay, so if I forget what it was, then I'll go to my little reference triangle, and my reference triangle might look like this. So I've got a 60-degree angle here, and I remember there was also, it was this 30-degree angle up here. And now, gee, I forget the values for the sides. I think it was 1, 2, and the square root of something, but I don't know exactly where they belong. Well, let's go back to the idea of our original discussion with this. Our original discussion started out with an equilateral triangle, a triangle in which all the angles are 60 degrees and all the sides are the same length. Okay, and then we bisected this rascal. We said, okay, if this was a 60-degree angle, then after we bisect, that's 30. Oh, here's our 60 right here. Here's our right angle. Now we just make the sides convenient. Now it's convenient to make this side 1, and therefore this is 1, and the whole thing is 2, and that's 2. So we have, oh, here we go. Now take all of this out in your imagination. We have 1, 2, and what's this? Well, if we need to, we can go to the Pythagorean relationship and figure it out. It turns out to be the square root of 3. So we have the 1, 2, square root of 3 triangle that we refer to in making our calculation. And we're thinking about, let's see, the cosine of 60 degrees, that's adjacent over hypotenuse, so it's 1/2. And therefore, the cosine of 4 pi over 3 is negative 1/2. Okay, so that's the way you kind of think through it. Let's go through it one more time. Let's use another one. Now, this one may seem even more imposing, the cosecant of 11 pi over 4. Well, we start the same way that we did with the other problem. You think cosecant and now separate a distinct coefficient from pi. We have 11/4 pi. All right, now, how many times does 4 go into 11? So we think cosecant of 4 into 11 goes 2 with 3 left over. So this is 2 and 3/4 pi. Now, what about on the coordinate plane? Well, let's see. We've got on the coordinate plane, I know that this is pi, there's 2 pi. That's either 0 or 2 pi. So I'm talking 2 and 3/4 pi. So 2 pi would be an angle all the way around to here, you see. And then 2 and another 3/4. 3/4. That's 3/4 of pi. Pi would put us back over here. 3/4 pi means 3/4 of that amount. Oh, that's about right in here. You see, so here's 2 and 3/4 pi. So our angle then falls into the second quadrant. All right, now, all right, what are we going to do about this? Well, we're going to create a reference triangle and a reference angle. Now what about the reference angle? We've got, we can throw out the 2 pi part of it and think about it like this. What's 3/4 pi? And the reference angle for that? Well, we take pi and subtract 3/4 pi. Oh, that leaves us with 1/4 pi, 1/4 pi, or pi over 4 for our reference angle. Oh, this is another one that I was supposed to remember. I forgot the relationship to angle measure in degrees, and so I might go to the side and do the same thing that we did on the previous problem. I might think, well, 180 degrees, whoops, excuse me, pi corresponds with 180 degrees. And pi over 4 then corresponds with 180 over 4. Let's see, that turns out to be 45 degrees. Oh, that was one of my handy-dandy reference angles and a little triangle that I can construct here. And that triangle looked something like this. Remember, if this is 45 degrees, then this other angle is 45 degrees. If the angles are the same, the sides opposite them are the same, so we made it easier on ourselves, 1, 1, and this turned out to be the square root of 2. Okay, oh happy day. We have now for the, let's see, we're talking cosecant. Uh-oh, I forgot now. I've got my reference triangle. I've got all of that. I need to know something about the sign here, and I need to think about the fraction that is cosecant. Okay, let's talk about the fraction first of all. Cosecant, maybe I forgot that the ratio that corresponding with cosecant. But I do know this, that cosecant, along with secant and along with cotangent, are all reciprocals of the primary 3 trig relationships. And you know, I forgot which one it's the reciprocal of. So what I could do is this. I could think, well, I know that they ran in a pattern that we had sine, cosine, tangent, and then cotangent, and then secant, and then cosecant. Oh, okay, and the reciprocal situation went like this. Okay, I remember that. Now, okay, so cosecant then is the reciprocal of sine. All right, good. Now, sine I know to be opposite over hypotenuse, so this is hypotenuse over opposite. So I'm talking about, let's see, hypotenuse over opposite. Now, if this is my reference angle, hypotenuse over opposite would be the square root of 2 over 1. So we're talking about the square root of 2 here. So the square root of 2. Now, I'm not going to put a sign here just yet. I may have jumped the gun a little bit in finding the value of the square root of 2, because I need to identify the sign in the second quadrant. But in the second quadrant, you know, if I'm talking about, let's see, adjacent over opposite, you see it's always positive over, oh, this y value is positive in the second quadrant, so cosecant is positive in the second quadrant. So just for emphasis, I'll put a plus here. All right, so anyway, that's the way you kind of think your way through these matters if you have forgotten some of the information. Let's go through another problem. This one says that if sine theta is 1/3 and theta is in quadrant 2, find cosine theta and tangent theta using identities. Now, we used identities in a similar way in a previous problem. But with that problem, we were confined to the first quadrant, so all the signs were positive. Now we're in quadrant 2, and we have that to consider as an extra bit of information in this problem. All right, so let's see. The sine of theta is 1/3. Theta is in quadrant 2. Now, if we want to cosine theta, and we want to use an identity, then we have to identify an identity involving cosine theta and sine theta. Well, that's the first Pythagorean identity. That's sine squared theta plus cosine squared theta is equal to 1. Fill in for sine theta is 1/2. So we have 1/2 squared. Now this is 1/9. So I'm subtracting 1/9 on both sides. And over here 1 minus 1/9 turns out to be 8/9. But if cosine squared theta is 8/9, then cosine theta is plus or minus the square root of 8/9. Then now in previous problems like this, we've just thrown this out and said we want the positive value. Sure we do, as long as we're in the first quadrant. But we're not in the first quadrant anymore. Which one of these do we want? That's the important question right now, along with taking care of this radical part. Well, let's see, cosine in the second quadrant. Now remember, cosine, let's see, cosine was adjacent over, okay, that's x. Okay, so it corresponds with how x rolls in the various quadrants. X in the second quadrant is negative. And so we're talking about the negative value here for this choice. And then the square root of 8. Well, 8 has a square in it. 8 is 4 times 2. The square root of the 4 is 2. 2 appears outside of the radical. The other 2 appears under the radical sign. So this is 2 root 2 in the numerator, and the square root of 9 is 3 for the denominator. So here's cosine theta. Now the analysis for tangent theta is easier. We have a handy identity. It's tangent theta is sine theta over cosine theta, and we have those values already calculated in the problem. Sine theta from up here is 1/3. Cosine theta we just calculated as negative 2 root 2 over 3. And now it's a little arithmetic kind of problem here. We know that our value here is going to be negative, so we could just bring down negative at this point if we want to. But here's what I did. I said that this complex fraction becomes 1/3 divided by this, but it means 1/3 times, boom, it's reciprocal. And now the 3's go out, and we have negative 1 over 2 root 2. Rationalizing, we find this to be negative root 2